Okay, good. So that's what I wanted to mention with regards to the logistics of the test. So let's start. Remember, what is in scope for the test is chapters 4, 5, 6, and 7. And expect to all any work that we cover during that time. Also, all the cracks up to last week will include in scope for this semester. Let's have a look at what is important for chapter 4. So with chapter 4, you can remember it was all about threads. Now, one of the first things to remember, or one thing that you should know from a structure point of view in the test itself, this question, or the questions based on chapter 4, is a total of 19 marks, 19. So, if there are 4 questions from the theory part, I have to kind of weigh it evenly. So, 3 of the chapters 4, 5, and 6 are 19 marks, and chapter 7 will be 18 marks. And the rest will be the practical stuff that you guys have. Okay, so with the 19 marks, what is important with regards to threads? Threads, not threads. Okay, first thing to remember is that in threads, there's a difference between a thread and a process. If we describe a process, each process has a memory address that it runs in, the start address and the end address is where physically you get its code, the data, and all of these things, all of these actions. Another thing that defines a process is things such as the number of open files, the list of open files that it has, the type of resources that's currently associated with this specific process. So there's a number of things that each process has unique. Also, the code that we find in the process, you get on a process level, together with the data, together with whatever files. But there are things that we associate with a thread that we only find in each thread. And that is, firstly, the set of registers. Each thread has its own set of registers associated while we're running that thread. Another thing that it defines per thread is things such as the stack. So not only do each thread has its own registers, it also has its own stack that you basically have. So make sure that you know what is unique to a thread, what is shared between threads, really what is on a process level, what is so forth. So this is an important aspect that you need to understand. Then another thing which is important is, why do we write multi-threaded applications? Why do we want to have this? So a number of benefits are, definitely it gives us responsiveness. Now what does that mean? It means that we can have things happening in our process while other things are blocking. So we basically get continuous execution when certain other things are blocked. Another thing is that we get what they call resource sharing. Is very simple. I mean, we've already seen here that registers share the same code. Share the same data. So typically things like global variables, very easily to share those things between your threads. Where if you do that in between processes, it's a lot more complicated. Remember in the previous chapter we all had everything about message passing and shared memory and all of that, which was a lot more complicated. Another thing is what we get is the economy. It is cheaper to spin up a thread than it is to spin up a whole process. Because with the whole process you have to assign a little number of memory for it, you have to keep track of what resources it's running, and all these things. Where if you just, with a thread, the only thing you need to the thread is the registers in the stack. So it's a lot less overhead to just spin up a thread, run that thread, and then you interact with the other threads rather than another process. And then obviously it gives us scalability. If we run a multi-threaded application on a uniprocessor system, then it doesn't really scale more than another well, much more than a multi-processors environment. Because with multi-threads, you can easily, when a process gets execution time, you can have multiple threads in that process running concurrently on other, or in parallel rather, on other cores. And it's a lot easier also to switch between threads than if you have to do a context switch between processes. I think that was also a big problem. Thread switching is lower overhead than context switching. So this is important to remember this. You have to understand what's the difference between concurrency versus parallel. Concurrency is where we describe the principle is where you can run multiple threads concurrently, but what it actually means is that each thread gets a bit of a time slice on the process. Where with parallelism, if we use that term in this textbook, then we say that we can run multiple threads at exactly the same time. How is that possible? Well, because we've got potentially different CPU cores or multiple CPUs in the system. So those are the differences between what is meant by concurrency and parallelism. Then we'll talk a little bit about some of the models in which we can implement threads. There are, in general, 3 different models that can be adopted by operating system developers when they implement threads in their systems. The first one is what they call the many-to-one, then there's the one-to-one, and the many-to-many. Basically, just review each of these. Many-to-one basically means that you can have multiple user-level threads running in your user space, but they all map to one thread running in the kernel. So the kernel scheduler, for instance, do not know about these multiple user-level threads, but the user-level threads, they can be individually scheduled using the runtime that they're in. Then you get the one-to-one model, and there we have a direct association between a user-level thread and a kernel-level thread. And then when we schedule our kernel-level threads, they have a direct effect on the user-level thread as well, because it basically allows each one to run at the same time. Your normal modern operating systems, such as Windows, Linux, Solaris, Higher, and so forth, they use this type of model. Just remember that. And then the last one is this what they call many-to-many model. Now, what is interesting with the many-to-many model is that in certain runtime environments, this model is actually illegal, where we have a certain number of user-level threads that gets mapped to a different number of threads on the kernel side. And what typically happens in between here is that we've got a runtime environment that manages that mapping and ensures that it runs. A good example here is typically if you run multiple Java processes on your computer, but they all run inside the same Java runtime, then typically the Java runtime machine will handle the user-level threads, which can be multiple, and the Java runtime machine can then map it to a certain number of kernel-level threads. So those are all possible. Another thing that's kind of fits in here is this same principle of thread pools. It also fits kind of with this type of model here. So anyway, that's not very important for that section. Okay, next is when we look at threads, we also talked about different ways in which we can implement threads. This is what they call implicit threading. With implicit threading, it basically means that we wanted to make it easy for developers to use multi-threaded systems. And I specifically demonstrated OpenMP. I showed you guys how we can use it with C++. Very, very simple. Create a system that can run a number of threads in parallel. In fact, when you've got a section that describes parallel, it basically will spin up a number of threads and it will run that code section in whatever number of cores you have inside yours, or let's call it virtual processors that you have inside your computer. And I demonstrated in my computer where you've got such a parallel section that it spinned up, I think, 8 of these threads on my computer because I had 4 cores, each one had a hyper-threading compiler to implement the running, and say, please